Hi, I'm Dennis and I'm going to present our work, Be Water My Friend, Mesh Assimilation. This is a surface reconstruction technique inspired by the ability of water to assimilate to any shape if being poured into it. Let's first briefly reassess the challenges in surface reconstruction. For example, to measure point cloud as it is acquired from a 3D scan, you have to overcome several artifacts. Here are the most prominent 5, as identified by Berger et al. In their latest survey from 2017. Issues may arise from misaligned scans if your object was captured from different angles and the partial scans do not align properly. As in any signal capturing pipeline, 3D scans are usually also not free from noise or outliers. We also have to deal with missing data if parts of the object were not covered during the scan, as well as with varying sampling density. We can also specify some quality criteria for our mesh. Desirable features, for example, are a uniform mesh structure with evenly distributed vertices and homogeneously shaped triangles. Furthermore, the reconstructed surface should capture smooth regions as faithfully as fine details and sharp feature edges. The watertightness of a mesh is important for further downstream applications, like 3D printing and volume rendering. Our reconstruction technique falls into the category of ballooning and shrink-wrapping approaches. A first of this kind was introduced in 2006 with competing fronts, where a growing mesh complex is placed in the target point cloud and approaches the target shape in a coarse-to-fine manner. Point-to-mesh uses a neural network to shrink-wrap a convex hull around the target point cloud. The approach in cooperative evolutions combines both methods, as they grow one mesh from the inside and shrink a second one from the outside. The result is extracted from the space between the two meshes. Our work is now a generalization of both concepts, as it is invariant of the initialization mesh. It can start from the inside and grow into the target shape, or enclose the target shape and converge on it from the outside. It is furthermore a generalization in terms of input data, as we can mesh several implicit geometry representations. This obviously includes 3D scan point clouds, but also binary image stacks as they are produced in MRT scans. We can also mesh signed distance fields or use our procedure for adaptive remeshing applications. As teased on in the title slide, our procedure is based on an iterative refinement process. Each iteration cycle consists of 5 steps, namely a refinement step to increase the mesh resolution where necessary, an equalization step to ensure mesh uniformity, the assimilation step in which the mesh grows and refines to the input, a step for mesh improvement operations, and finally the topology adaptation to objects with higher genus. Now I'm going through each step with more detail, starting with the refinement. As the mesh grows during the optimization, it is constantly refined by increasing the resolution where necessary. Therefore, the algorithm identifies the vertex with the largest average edge length in its one-ring neighborhood. This triangle fan is then replaced with subdivided geometry. We use the square root 3 subdivision scheme and compute new vertices based on point normal triangle interpolations. This is suitable for flat regions as well as curved and angled geometry. In the equalization step, each vertex strives to equalize the distance to its one-ring neighbors. The displacement vector E computes as the average position of Vi located on its adjacent edges, but at an average edge length distance to its neighbors. Now to step 3, the assimilation. This is actually a twofold operation, as a mesh vertex is either in growth mode or projection mode. Therefore, each mesh vertex evaluates the distance to its closest point cloud neighbors. If the distance is too far, the vertex is in growth mode. If the distance is close enough, it is ready for projection. In the very beginning, and also in this example, all vertices usually start in growth mode. Each iteration, we re-evaluate the distances for all vertices. Now, one vertex is already close enough to the surface and independently can transition into projection mode. As the iteration progresses, more and more vertices transition into projection mode. Simultaneously, the mesh is also constantly refined and introduces more vertices. Eventually, when the mesh covers the whole object, all vertices are in projection mode. Formally expressed, the assimilation vector A formulates like this. Growth simply uses the vertex normal, scaled by an averaged edge length in its local neighborhood, and oriented by O, which determines if the vertex moves outwards or inwards. The projection is a bit more tricky, but we get to this in the next slide. For this example, we now assume that the vertices are close enough and we want to project the mesh surface into the point cloud, resulting in something like this. As projection space, we use splat disks, which are centered on point cloud samples and oriented orthogonal to their normal. A simple combination of projection directions is not very practical. A more suitable solution would look something like this. Vertices on flat regions move straight outwards, whereas vertices on edges and corners are attracted by tangent space intersections. A key contribution here is the way we compute the weights for the combination of projection directions. The weights are a bilateral combination of a distance component and an angular component. The first component decreases the weights inversely to an increasing distance to the closest points on a corresponding splat disk. The angular component computes as the dot product between mesh vertex normal and point cloud normal. With close to parallel directions, the dot product is close to 1. With almost orthogonal orientations, the weight approaches 0. For normals pointing into opposite directions, the dot product would be negative but is then clipped to 0. This allows for vertices on flat surfaces to be projected onto flat regions, whereas vertices on corners and edges are attracted equally from both sides of the edge, and are therefore drawn into the intersection of the tangent space. Now to step 4, mesh improvement operations. Cases like these may occur during the mesh development, as the other optimization steps are only focused on the position of the vertices, but do not care for the way they are connected. Nevertheless, we can easily identify these scenarios and fix them. The blue and green cases are concave and convex edges that stand out in contrast to their direct triangle neighbors. They are easily fixed by rotating the affected edge. Very short edges, like the red one, may occur after such rotations and are also easily fixed by collapsing the edge to a single vertex. Step 5 handles the adaptation to a certain object topology. For example, our initialization mesh starts with a genus 0. But if the target object has a higher genus, our mesh can adapt. Therefore, we detect mesh regions growing onto each other before they collide. Corresponding patches on both sides are cut out and stitched back together by inserting tunnels. This can occur multiple times during the assimilation. In between, the iteration continues as usual. Now this completes one cycle of our iteration process. The equalization and assimilation steps are realized on the GPU, as the operations are executed for all vertices in parallel. The refinement and improvement steps modify the mesh topology and only interleave the fast GPU steps when they are needed. The topology adaptation step is optional. If the genus of the target object is known to be 0 beforehand, it can simply be omitted in the iteration. Now let's have a look at some results. Here we conducted a large bulk comparison on the Thingi 10K dataset and compared our results to common surface reconstruction techniques. The ground truth object is shown on the bottom right, our mesh assimilation result right next to it. What stands out here is that our result is the only one that accurately captured the sharp threads of the screw and really nicely reconstructed the embossed logo on the screw's head. The artifacts we can see in our result on rounded features of the object are even more exaggerated on the following example. This is caused by our projection method, as vertices are drawn into the intersections of the tangent space. For convex curved surfaces, linear tangents intersect outside of the object. For concave curved surfaces, they intersect on the inside. However, on CAD-like objects, we can clearly see the advantages of our approach. Our results are the only ones to accurately capture sharp feature edges, as our mesh unravels without a smoothness prior. To look at some numbers, we evaluated this benchmark with several error measures, listed here as average and median over all objects. The compared errors include the Hausdorff distance, the root mean squared error, surface area deviation, total volume deviation, normal angle deviation, and water tightness. We can see that our method outperforms the established state-of-the-art in almost all categories and comes close to the first place in the rest. The reason we rank second and third in these categories can be attributed to some failure cases. If parts of the anticipated objects are thinner than our target edge length, the mesh expansion comes to a halt and parts of the object remain unexplored. This is very rare, but as the Hausdorff distance only accounts for maxima, it results in quite drastic errors. Here we again compare these numbers visually, where our results are listed in blue, and again emphasize the achieved improvements. An official implementation of competing ballooning approaches was only available for point-to-mesh. However, the qualitative comparison on this example object also highlights the improved levels of accuracy that can be achieved with our method. To conclude, in the beginning I've listed several artifacts a reconstruction technique has to overcome and define some properties that we want to achieve with our method. Our projection technique is based on closest point cloud neighbors. The bilateral weighting scheme is based on distance and angular components. Therefore, it is robust to several artifacts, guarantees epsilon closed reconstructions while maintaining sharp feature edges. For missing data, we have experimented with these examples and cut out portions of the twist tube and removed 75% of the head's surface cut out in randomly shaped patches. Here we can see the randomly sampled splat disks on the remaining surface. The reconstruction smoothly interpolates the missing data without growing through the holes. The algorithm starts on a watertight mesh, and as there is no operation that violates the mesh's integrity, we also end up with a watertight result. For varying sampling density, we have importance sampled this object based on surface curvature. High curvature facial features are sampled more densely than the low curvature portions of the head. By default, our method will strive for equal edge length and produce a uniform mesh result. However, we can also link the target edge length locally to the splat disk radii. Then we can produce a mesh where the resolution is adaptive to the sampling density. And as listed in the beginning, we can not only remesh existing objects or reconstruct point clouds, but also generate surfaces for signed distance fields and binary volumes. The only operation we have to adapt is step 3 of our iteration cycle. As shown with step 5, the mesh can adapt to objects of higher genus and reconstruct objects with complex topology. In our benchmark, we found that our method produces superior results compared to the state-of-the-art, especially in terms of overall sharpness and accuracy on fine details. With this, I conclude my presentation and thank you very much for the attention.